research professor in the Knight Foundation School of Computer Science and FIU. Dr. Ibarra is the Assistant VP of Technology Augmented Research and also responsible for the Center for Internet Augmented Research and Assessment. He is leading 2 unique NSF awards called AmPath and AmLight. And Dr. Ibarra's research interests include software-defined networks, network architecture and automation, and network control and management. Dr. Ibarra, thanks again for accepting our invitation. The floor is yours.
Thank you very much for having me and for the opportunity to present at the Knight Foundation School of Computing and Information Sciences seminar series. The topic of my talk, as you mentioned, is the AmLight Express and Protect network. The AmLight network operates as an international production network and platform for network innovation, supporting research and education. That's the main theme of my talk. This will be the outline that I'll use for my talk today. My objective is for you all to gain an understanding of AmLight as a production, research, and education network, and how we're using AmLight's resources for network innovation, and also how AmLight is responding to challenges from science applications. I'll start by giving you an introduction to Sierra, the home of AmLight at FIU, followed by some history about the AmLight project. AmLight is managed from the Center for Internet Augmented Research and Assessment. Sierra is an interdisciplinary center. It supports and conducts research and education through the application of advanced cyber infrastructure. Sierra consists of a small group of network engineers, software developers, and a support team. On the lower right, you see a recent photo of the Sierra team. Some of the goals at Sierra are to bridge technology gaps between researchers and IT practitioners. One of my roles is to leverage the expertise in the Division of IT and also at the School of Computing and Information Sciences to better inform our community about AmLight and other projects at Sierra. Another goal is to invigorate scholarship for undergraduate and graduate students. Engaging students to participate in projects is one of our core activities. Last year, we had 19 students participate in projects at Sierra. Sierra is 100% contracts and grants funded. 71% of our funding comes from grants and 29% from contracts. And finally, Sierra aligns with FIU's goals as a public research university, contributing to its research, scholarship, and technology development. Let me transition to give you some history about AmLight. So AmLight was established in 2010 under an NSF International Research Network Connections Award. AmLight consists of a 20-year build-out that includes connections to research and education networks in Latin America. FIU led the effort to link the US research and education networks to Latin America in collaboration with Internet2 and industry collaborators. Back in like early 2000s or even late 1900s, the Division of IT collaborated with computer science on its first high-performance networking proposal to the National Science Foundation, which is how we got started with Internet2. So there's a lot of history between computer science and AmPath. And so this collaboration resulted in the creation of AmPath as an international exchange point in Miami in 2000. AmLight was one of the first projects to use optical spectrum combined with lease capacity on its backbone. Long-term leases on the optical spectrum was a key accomplishment. We have leases that run until 2032. And these resources provide significant value to US science facilities that operate in Chile, in South America, and also we have our sites towards Antarctica to be able to connect to our network. AmLight was one of the first to deploy and operate its production network with software-defined networking since 2014. SDN enabled dynamic service provisioning and significantly increased our operational efficiency. We also established the South American Astronomy Coordination Committee, we refer to as SAC. SAC provides a venue for the exchange of information and coordination between the US astronomy projects in Chile and the AmLight network operators that run the networks in Latin America and the US. The SAC is in its 11th year. We had our 2021 SAC meeting and hosted 61 participants. And the report is available online if you're interested in taking a look at what we're doing in that group. So next, let's take a look at AmLight as it is today. It operates as an international production, research, and education network. So this is a representation of the AmLight production network. The network map shows AmLight's footprint in the US, Latin America, and Africa. The AmLight Express ring, shown in green, consists of multiple 200 gigabit segments that connect Boca Raton to Sao Paulo, Boca Raton to Fortaleza, Sao Paulo to Fortaleza. We have a 100 gigabit connection from Boca Raton to Cape Town, South Africa, and a 100 gigabit connection from Santiago to Porto Alegre. The 100 gigabit AmLight Protect ring that you see in red carries primary traffic as well as serve as protection to the Express network. It consists of the following city pairs between Miami, Fortaleza, Fortaleza, Sao Paulo, Sao Paulo, Santiago, Santiago, Panama, Panama, San Juan, and San Juan back to Miami. The aggregate upstream capacity is currently at 600 gigabits per second, and we have open exchange points operating in Miami, Fortaleza, Sao Paulo, Santiago, Cape Town. And this is a significant infrastructure to support science and education between the US and Latin America and Africa. So this next slide represents the 5-year plan we have for the AmLight backbone. I've described the 2020 map shown on the leftmost side. The 2021-2023 map in the middle shows some of the work that we have already ongoing. In 2021, 2 by 100 gigabit connections connected Fortaleza to Portugal, that you see here. And we also have activities going on to connect from Fortaleza to Sao Paulo here to strengthen the backbone. That's in collaboration with our partner in Brazil, RNP. And we also have, so by adding these two segments, that will increase the capacity of the network to 800 gigabits per second. That's planned for up to 2023. Then as we move to 2024 through 2026, these are some of the plans that we have represented with these dashed segments. We have the regional network of Latin America, Red Clara, that is adding capacity between Barranquilla, Colombia to Panama, and then this will add new routes between the US, Chile, and Panama for resiliency. These are all the partners that are involved with the AmLight project. We have a number of different organizations in Latin America, as well as in Florida and Internet2 in the US. So up to this point, I presented the AmLight network infrastructure, its links, aggregation points, and bandwidth capacity as it is today, and the enhancements planned to increase capacity and resiliency. Next, I would like to introduce a technology we refer to as In-band Network Telemetry, abbreviated as INT. INT is currently a production service on AmLight. but we also consider it one of our most significant innovations. So I'll start by describing a challenge and reasons for the use of in-band network telemetry. So isolating and detecting faults of data transfers in long-haul networks that have high latency, such as AmLight, can be complex and time-consuming. It's both a technical challenge and a social challenge because isolating and detecting faults is constrained by lack of visibility across different networks. So as a result, detecting what events cause performance degradation often results in questions that have incomplete answers. For example, we don't really know where there's packet loss occurring and why, or which path the packet took, how much time a packet queued at each switch. So effectively, there's a lack of tools that provide enough visibility to detect these kinds of faults. This slide shows network monitoring pain points that we have when attempting to detect these network transient events. So common network monitoring tools fail to detect network transient events. Tools we've used for many years are quite limited. For example, the SNM-based tools that we've used to measure performance are just inadequate for being able to provide the visibility of what's going on within the network. Network transient events are essentially short-term and sporadic degradations in network performance. They're caused by conditions that can lead to failures over time. For example, attenuation on an optical channel. These kinds of events often go undetected. Microbursts is another one of these types of events. So what results in causing a microburst? Typically, it's a data transfer that's so short in the time domain that monitoring tools just cannot detect it. And I'll go into a little bit more about what I mean by that. They can be malicious or not, and they're not easy to detect. Time scale could be as low as hundreds of nanoseconds to tens of microseconds. Microbursts can also have a high impact, causing packet loss in long-haul networks with high latency, such as AmLight. So what's AmLight's solution to network transient events? The solution we've adopted is a technology we call In-band Network Telemetry. And this slide describes what INT is and what it does. So INT records network telemetry information in a packet. So while the packet traverses a path between 2 points in the network. What is network telemetry information? So essentially, it's a snapshot of the state of the network provided as metadata. So this snapshot occurs as the packet moves from one state to another within the data plane of the network. Telemetry reports are exported directly from the data plane with no impact to the control plane. And this is very important for performance reasons. INT tracks and monitors and evaluates every single packet at line rate and in real time. So having this capability of being able to work in real time allows us to achieve the deep visibility we need in the network to be able to detect transient events and microbursts. Some examples of network telemetry information collected are timestamp, Ingress port, Egress port, queue buffer utilization, sequence number, and many others. As a result, visibility of the network state is unprecedented. The telemetry data is available to detect throughput issues due to bottlenecks, failures, or configuration errors. So let me give you an example of how INT works. And this is an example of a network that's instrumented with INT. So let's start here on the left. You have a source node at the left of the diagram here. It sends a packet, and this packet is completely unaware of INT and that INT is enabled in this network here with these 5 switches. So the job of the INT source switch, the first one here, the source switch, is to push an INT header and metadata into the packet, shown here in this first packet representation. Every INT switch in the network then pushes its metadata into the packet. You can see here telemetry 2 was added, telemetry 3, telemetry 4, telemetry 5, as the packet moves across the data plane here through the switches. If a switch is not INT enabled, it'll just forward the packet. It just ignores the INT content. When we get to the sync switch here at the very end, the job of this INT sync switch is to extract the telemetry information from the packet, then forward the original packet to the sync node, which is over here on the right, this node. And then the INT sync switch then forwards each telemetry report here to a server we call the INT, or an application we call the telemetry collector. Okay, and this here is the report from all of these telemetry reports here that's sent to the collector. The telemetry collector then receives, parses, processes, and generates operational telemetry reports that then get interpreted to give us the information we're looking for. So basically, this is how INT works. And this slide here is a representation of a telemetry report with metadata and data. So you see here all the metadata that is available per switch as well as per report. And we're collecting all of this and then processing it to be able to give us information about different events and metrics that we want to measure. So let me give you some examples here. In these next slides, there are examples of how we're using the metadata and achieving granular visibility using the INT technology. So in this case here, we have instantaneous Ingress and Egress interface utilization. The telemetry collector reports Egress interface utilization every 100 milliseconds. And this is useful for detecting microbursts. We can see the start and end of microbursts here in this graph. These spikes that you see here are classified as microbursts. The spikes that are over 40 gigabits, right here. The spikes that are below, under 20 gigabits, we classify them as normal traffic. But typically, we cannot see these kinds of events with the traditional tools that we've been using so far because they work in a much smaller time domain that those tools operate in. Another metric that we're now measuring is instantaneous egress interface buffer utilization. We're now able to measure this on a per port for every switch. We're using this data to evaluate QoS policies and to detect sources of packet drops. Note the difference in the vertical scale between normal buffer utilization and buffers that are under congestion. So the graph on the left here, the scale you can see is in kilobytes. And on the right, it's in megabytes. So here, the representation shows what the buffer looks like under normal utilization. And once it goes about over 200 kilobytes, we start to see congestion building up. And that starts to lead to potential packet drops. Okay, so you can really see the difference here as the scale changes from kilobytes to megabytes. And we've been able to detect that 200 kilobytes is the threshold of when you start approaching congestion in the buffers. This next metadata allows us to monitor per hop, per packet forwarding delay. It's useful for finding sources of jitter along the path. Jitter refers to variation in packet delay. So the graph on the left shows normal buffer utilization, and the graph on the right shows congested buffers. The vertical axis represents delay. And note that under normal buffer utilization, delay was measured in microseconds over here in this graph showing the normal utilization. Under congested buffers, delay was measured in milliseconds. You can see that here, for example, as these spikes start to occur when the buffers are under congestion. So to give you an idea of what this means, consider the degree of delay in the right graph here. Some of the packets were buffered for approximately 65 milliseconds in this particular time zone here. So that's about how long a packet takes to transit from São Paulo to Atlanta, to give you an idea of how long that packet was in that switch. Now, to sum up from every example I've shown here, this is a use case of an experiment that we did to compare INT with SNMP, reproducing an event of microbursts on a 100 gigabit link. The experiment transmits 5 bursts of 40 to 50 gigabits per second for 5 seconds. The top graph, it represents an INT switch exporting metadata in real time per packet. And the INT graph shows 5 spikes lasting 5 seconds, each generating 38 to 50 gigabits of traffic. And these spikes are, as defined earlier, classified as microbursts. On the other hand, if you look at the bottom graph, it represents an Ethernet switch that's polling with SNMP, and it's polling at its maximum rate of every 15 seconds. The SNMP graph shows 2 spikes lasting 30 plus seconds with peaks of utilization of 13 gigabits per second. They are not reported as microbursts because they're not within that small domain threshold. So what we could see here with these 2 graphs is that the INT graph is more realistic. It's a more realistic representation of network events. An important conclusion to consider, though, is that a legacy protocol such as SNMP is not enough to characterize the microbursts and determine their impact. From another perspective, SNMP reported that the utilization of the 100 gigabit link was at most 13 gigabits per second, giving a false impression there's more available bandwidth. So when you're working with SNMP, clearly other tools will be needed in addition to SNMP to accurately characterize the events on the network. But more importantly, if you're going to try to, if a science project is going to try to determine how much bandwidth capacity it needs, using SNMP tools is not going to be accurate enough to really let it know how much bandwidth is going to be required. So this experiment confirmed for us that observing microbursts becomes a lot more straightforward when your monitoring tool allows you to have more visibility of network events. So up to this point, I've provided reasons why AmLight was an early adopter of INT, how it works, what INT metadata AmLight uses for deeper visibility into the network, to improve operations and to support the research and education communities using AmLight. And we did a comparison of INT and SNMP for measuring microbursts. In the next section, I'll present how Sierra, the work it's doing with another project called Atlantic Wave SDX, that we use to increase visibility across multiple network domains. Because up to now, I've just been talking about the use of INT on AmLight, but we need to have ways of looking into other networks and be able to also increase the automation of the network operation. So I'll start off by framing the challenge that we have with this project. So INT provides deep visibility in the AmLight domain. We've covered that so far. I presented what INT is and how we've instrumented AmLight to provide that deep visibility. However, production science network flows cross multiple network domains. Most often where data is gathered and where it's analyzed is geographically far apart. So multiple networks are involved in transporting the data from source to destination. So we know that there's a lack of visibility of what happens to packets as they traverse multiple network domains to reach their destination. So unlike AmLight, networks normally are not instrumented with INT. Granular visibility is lost when packets ingress into other network domains. It's important to improve the visibility of the state of each packet along the end-to-end path. So why is it important to improve the visibility of the network state? So what if microbursts start to occur in a network domain that impacts the data transfer of a delay-sensitive science application? How can the network respond quickly in real time to minimize the impact to science operations? I'll now present what AmLight is doing to collaborate with other R&D networks, research and education networks, to increase visibility across multiple network domains. One of the terms used in research and education networking, the research community, is to refer to the lack of visibility across networks is the interdomain challenge. The software-defined networking paradigm was adopted to address the interdomain challenge by research and education network operators. In this slide, I'll cover contributions made by Sierra to respond to this challenge. So in 2014, a number of innovations occurred to illuminate possible opportunities to respond to the interdomain challenge. The concept of software-defined exchange was introduced. There's a paper by Gupta that introduces the concept, and it became a very important paper in the community to be able to understand how open exchange points can be enhanced with software-defined networking. Research and education networks normally connect at open exchange points, like, for example, AmPath. And by 2014, the AmLight network was SDN enabled. Therefore, services such as provisioning and other services performed by AmLight became more efficient. So in 2015, FIU, in collaboration with Georgia Tech and UNC Chapel Hill, a group there called RENCI, and USC ISI, we started the Atlantic Wave SDX project. Here is the NSF award number. And the project involves software that was developed and open exchange points, such as AmPath, to enhance them to operate as software-defined exchanges. In other words, the SDXs offer, what this project did was to offer the SDXs a lot more capabilities than just operating as exchange points to provide Ethernet interconnects as a means by which networks can peer. The SDXs enabled them to offer more flexibility as allowed by the software-defined network paradigm, such as enabling network programmability and network virtualization. So we were able to develop a number of new services for providing interdomain point-to-point and point-to-multipoint circuits with bandwidth guarantees, provided a simple web-based and REST API user interfaces for users and applications, and to support a variety of southbound protocols for connecting different types of devices. So this was the first iteration of our project with SDXs and telemetry. And now we have a new award, still called Atlantic Wave SDX, that started in 2020 to improve the work that we've been doing and to take the SDX and AmLight to a production quality level. So the major goal of the project is to improve the features of the SDX to production quality. We're adding capabilities to react to unplanned network conditions, changes and events, for example, the microbursts or attenuation on an optical channel, automating configurations, failure handling, and other management functions, in particular reducing dependency on human administrators and centralized management systems, adding support for layer 3 VPNs, increasing support of heterogeneous open exchange points and users by supporting additional southbound interfaces. Also, a very important part of the project is to integrate with national and international computing and data resources for example, the open science grid, and also adding fault tolerance, monitoring, and management functions for production use. And I'll explain a little bit more about what we mean in the next slides. So one of the ways that we're looking at increasing production use is by adopting autonomic networking functions and being able to create what we call a closed loop network orchestration system. So with closed loop network orchestration, we're going to implement self-management functions. And this is part of the specifications for autonomic networking that are published by the IETF. And it's comprised of self-start properties such as self-configuration, self-healing, self-optimizing, and self-protection. So the goals are to implement autonomic network functions to reduce dependencies on network operators and the centralized management systems, and to enable AmLight and SDXs to adapt to a changing environment, which is just the nature of networks that's constantly changing based on events that are occurring on them. So AmLight's aim is to increase automation of the traffic engineering and network tuning, and be able to do this in real time by leveraging the In-band Network Telemetry system. So by coupling the real-time visibility of the network state provided by INT and the programmable functionality of the XDXs that we've been developing, the networks can better respond to the requirements of science workflows. And I'll have an example to show what I mean by that. So this slide shows how AmLight is implementing autonomic network operations to achieve production quality. The closed loop network orchestration, as shown here in this simple figure, creates a continuous and repeating cycle of communications between the network infrastructure and the software elements. So the green represents the hardware elements, and the blue are the software elements. So we have an autonomic control loop connecting the autonomic functions and the autonomic nodes right here. So the monitoring process that we have collects network state events and telemetry reports. These are collected here by the data plane, and it's collected on a per packet level. The telemetry data is then exported to the telemetry collector. If you recall from how the INT telemetry works, you have the telemetry collector, and here these reports are aggregated for analysis. Then the current network state and desired network states are compared with the policies that have been defined for the particular network application that is using the network. Traffic policies then determine if actions are to be applied, and that's done here at this state. If there's any anomalies found or nonconformity occurs, then corresponding actions are sent from the traffic policy component to the SDN orchestrator in the form of intents and network instructions. Excuse me. The SDN orchestrator then interprets the intents and reconfigures the autonomic nodes that you see here in green by pushing instructions and configuration changes to the network components in the data plane. And then this process repeats for all the packets that are traversing the network. So this way, if some policy is beyond its threshold range, some actions will occur. So for example, if we have a policy that says to steer high priority network flows away from over provisioned links, one of the implementations that we're doing is to implement the policy that sets the threshold for outgoing interface queue occupancy, as we showed in the previous slides when we were showing the metrics. If the queue occupancy is over 80%, for example, and for more than 500 milliseconds, then the SDN orchestrator that you see here under autonomic control can execute an action without operator intervention to steer the network flows to a different queue. And this can be done in real time, or as close to real time as possible. And this is really important for some of the science applications that we're working with. And I'll have an example about that. So in this slide here, very busy slide, but I wanted to show it to you because it reflects the architecture of the SDX that we're developing and all the stakeholders that are involved with the project. The legend and the colors identify the stakeholders and the communities, and the colors also identify the stakeholders and the architecture components that they are contributing. So we have quite a few different groups involved with the project. So let me recap from the previous section. So we discussed the Interdomain challenge and our response to it. We introduced the Atlantic Wave SDX project and presented the work Sierra is doing with its collaborators on doing what it's doing to raise the production quality of AmLight and the SDXs in the Atlantic Wave SDX project. Next, let's take a look at how we're applying these innovations on AmLight as a production network to support science. So I'll start with an SLA-driven use case, the Vera Rubin Observatory. This is and what I mean by SLA is SLA is service level agreement. So in the context of the Vera Rubin Observatory, it means that the AmLight network is being instrumented to support its science workflow requirements, which is work that we're currently doing. So let me give you some context about the Vera Rubin telescope. It's a large aperture, wide field, ground-based optical telescope that is under construction in northern Chile. The telescope is an 8.4 meter telescope that will take a picture of the southern sky every 27 seconds, and it will produce a 13 gigabyte data set. Each data set must be transferred to the US data facility at the Stanford Linear Accelerator, SLAC in Menlo Park, California. It must be done within 5 seconds, and it's inside the 27-second transfer window. So some of the challenges that we're facing in responding to the SLA, the primary network challenge we have is that the Rubin Observatory will face high propagation delay in its end-to-end path. And this is because of the distance that we're working with. The round trip time from the base station in La Serena, Chile, which is in northern Chile, right up here, you can see, and the traffic has to go south to Santiago to get into the international backbone. From the base station to the US data facility at SLAC is approximately 180 plus milliseconds. We've computed that a 0.001% of packet loss will compromise a Rubin Observatory application. And this is a big problem because if we start having packet loss, we will not be compliant with the SLA requirement. So for a better understanding of the Vera Rubin Observatory use case, let's consider the following scenario. So in this slide that you see here, it represents the Vera Rubin workflow cadence. You have 27 seconds for the data set transfer window, okay? 22 seconds to gather and process the image, and that's shown here in white. And then 5 seconds for the transfer to the US data facility, that's shown in blue. And the telescope needs at least 40 gigabits per second of dedicated bandwidth to achieve the data set transfer within 5 seconds. The Vera Rubin Observatory network will be operated by multiple research and education network operators. As I mentioned before, we don't cover the entire network for Vera Rubin. There's multiple network operators involved in the end-to-end path. So this is essentially a distributed multi-domain network that we're working with. So what happens because of this? The troubleshooting, if we have to do any troubleshooting on this network, without the proper instrumentation, it becomes a very complex and time-consuming effort. So let's look at a scenario, what if a condition occurs that results in a packet loss? And that's shown here with this yellow box. The network then must react within the 22 seconds of the next data set process window, right here, in this white. It's likely the condition will impact the following data transfer windows, these red squares that you see here, and the following ones too. So depending on the type of issue, for example, if it's a packet loss or other kinds of soft issues that are not like a hardware issue that you can quickly detect where the failure is, it could take hours, days, and possibly weeks to mitigate the problem. If you remember earlier when I introduced INT, this is one of the reasons why INT is so important, is because often when you don't have that kind of visibility, you're really guessing as to where to start to look for it, okay, for the problem. So the impact to Vera Rubin can be costly and delay science that depends on timely access to data sets. So how is AmLight responding to the SLA requirements of the Vera Rubin Observatory? So this slide shows the instrumentation at each software-defined exchange in support of the Vera Rubin SLA. And you see this here in this figure that we have in Chile, Brazil, Florida, and Georgia. Express and Protect paths are instrumented with INT and Pulse Sonar, which is a measurement tool, from Santiago, Chile, all the way to Georgia, where we hand off to the ESNet network. So here you see in the management network, the management plane, the resources that we have connected to the data plane, which shows the Express network in green and the Protect network in red. So this management plane is processing telemetry reports, isolating and detecting traffic anomalies, validating performance thresholds, and computing risk profiles of both the optical links and the IP layer metrics. So it's doing this for every packet, as well as for everything it senses at the optical layer. So if a transient event were to occur, such as the microburst occurring during a dataset transfer window, packet loss might impact one transfer window, maybe let's say in Chile or in Brazil, and we will be able to detect the event in the telemetry reports that's processed by the management plane. We will then issue instructions to program the data plane to provision an alternate path before the next data set transfer window. And because of the closed loop orchestration, this process will repeat for every packet as it traverses the network. So we'll be able to arrest this before we miss the next transfer window. As a result, the instrumentation at each SDX, AmLight should not miss the next dataset transfer window, which is the metrics of success that we have for this project, is to not miss a data transfer window because we now have the deep visibility that we need through the In-band Network Telemetry technology. So I presented how the telemetry and measurement instrumentation on the AmLight network is supporting an SLA-driven science driver such as the Vera Rubin Observatory. But now let's take a look at some of our challenges going forward. So a telemetry report is generated for every packet, as I've explained. Receiving and storing hundreds of kilopackets per second can be challenging and also very costly. For example, without filtering the telemetry reports, the telemetry collector, which is a powerful server, its resources can be very quickly depleted. So what data to store and for how long is another challenge. So consider the Vera Rubin telescope with its 5-second bursts of 9 kilobyte packets transmitting at 40 gigabits per second. Each 5-second burst generates 487 kilopackets per second and a total of 600 megabytes of telemetry data to be processed and stored. One night's observation will generate 600 gigabytes of telemetry data. More than 190 terabytes of telemetry data will be generated every year to support the Vera Rubin Observatory. So we believe network telemetry data could be useful to network researchers. However, to collect, store, and process telemetry data to support research, for us right now, it's rather unclear how we'll be able to do this. Vera Rubin, it'll mainly be the network operators making use of the telemetry data, but the telemetry data is, I think, something that could be very useful for network researchers. And so part of what we're doing as some potential, some ideas to respond to these challenges is we're looking at data science and machine learning. They're powerful approaches to explore the INT telemetry data sets. We've been sharing experiences with network researchers at Lawrence Berkeley National Labs on the application of data science and machine learning to efficiently interpret INT data sets. Capacity planning and network optimization are areas Sierra is exploring for the use of telemetry data. Machine learning and other AI strategies can be employed to detect malicious traffic. For example, distributed denial of service attacks and single packet attacks and scans. We have a collaboration with University of Memphis in this area. An approach we're using and investigating is to correlate telemetry data sets with threat intelligence databases. This could lead to improving cybersecurity reports, resulting in the recognition of cybersecurity trends. So finally, Sierra is very interested and welcomes the opportunity to collaborate with the faculty and the students at the School of Computing and Information Sciences on potential research using the telemetry data that we've been collecting. So if there's any interest from the faculty attending today or your students, please let me know. But thank you very much for your time.
Great. Thank you so much for an interesting talk. Any questions?